Okay, it's a great pleasure to welcome Anton Mellit, who will tell us about some extra structures in Khovanov-Rozansky homology. Take it away.
Okay, so I forgot to. So this is based. So the results are in the paper with these people based on trying to work with Eugene and Matt. But today I want to spend some time on talking about some geometric motivation and sort of motivation. So and intuition. So we have some notations. Usually will be like L is a link, and usually it will be a closure of a braid of beta, and then C will be the number of connected components. And will be the and for so beta is in the braid group of n strands, and pi will denote the permutation for beta. So pi is an SN. So that's whenever I just bring up some L or some beta, you will know what I'm talking about. But okay, so I want to start by explaining some kind of graphical calculus for some kind of TQFT like calculus for this braid variety. So for braid varieties, character varieties, and so on. And so if you want, what is this braid varieties? I learned about them from the work of Schande, Truman, Zaslov. So you can read it there. There is some paper of Kalman, and then there is this paper of Eugene and others. But I didn't read it, so I just sorry. Anyway, so there is this thing called braid varieties, and this is sort of not really fixed object. It's sort of still being formulated, probably. But for me, I thought it is very natural that they appear in knot theory. So here is some small insight. Is that if you have so a Homfly polynomial can be defined as a trace on the Hecke algebra, right? You represent your braid as I map it to the Hecke algebra and then take the trace, Markov trace, and that Hecke algebra. I always learned it as an algebra of double cosets over a finite field. So somehow people sometimes usually learn Hecke algebra by giving some generators and relations, but I didn't even sort of know that part. I always thought that this is coming from the finite, from G over FQ over B of Q. So G is GLN, and B is upper triangular matrices. So this is a ring. So sort of you consider some formal linear combinations, and this is ring, and this Hecke algebra it's roughly speaking, so that's isomorphic to the Hecke algebra, where Q corresponds to the parameter in the Hecke algebra. And then things like such crossing correspond to some cells, certain cell in this GR of Q. So, well, right. So B equivalent cell, and so it's very natural to, instead of looking at points, so whenever you do this, take products in this ring, you can interpret this product as some kind of counting points over a finite field, and then you can ask, what is there some variety on which you are counting points, and you will get this braid variety. So yeah, variety over which to count points as this braid variety. So that's some little insight. Now let's be more precise. So so this is graphical calculus where right, G is always G is GLN, B is this upper triangular matrices, and W will be Sn. So what do you do is, first you should describe some markings. When you see a point, so markings on some kind of polygonal surface, marking on a polygonal surface. This is what we want to explain. So what is in the points? So polygonal surface will have some vertices, some edges, and some polygons whose boundary is the edge. So it's like a graph plus some polygons glued on top. And what is this marking? So to the points, we associate some, usually we associate some groups. And usually B, but can be more than. Right? Then what do you associate to edges? If you have edge and you have 2 points here, so for instance, B and B, then you want to associate some space on which B times B. So if you have 2 different groups, it will be left action of one group and right action of another group. And then, group. So this is some group, B, and this is some space, sorry, Z. So space Z, on which EBX. And then we want some more, plus we want to have a map from Z to G, which is BB equivariant. And that can tell us how to define things on polygons. So on the polygons, then there's no, sorry, no, that's it. So no marking. But polygons, instead we will associate a condition that, so we have this B, Z1, Z2, Z3, and so on. And this polygon means that we will look at points Z1 in Z1, Z2 in Z2, such that the product of this the i's in G, yeah, so you send this them to G by this map, is identity, is 1. So this is very intuitive. If you think about some kind of local system, some vector space which varies continuously, then in every point you can choose a basis. In the points you will choose basis, and then on the for each edge you will have a transformation matrix from one basis to another, and then there will be gauge renormalizations, like changing different bases. That means you act by this group B on the transformation matrix Z. And so given this kind of a polygonal surface with this markings, we define so let's call it a global quotient stack. So what is a global quotient stack? It just means a space with its group action. So E space X and some other group. That's now I'm in trouble. Gamma, yeah, gamma. In gamma, a group acting on X. So it just for me, global quotient stack is the same thing as a pair. It's denoted by X not gamma. And how is it defined? So gamma is just the product of this B's sitting in general. So V is a vertex, and you have this group V is a group associated to the vertex. Group at V, and X sits inside the product over edges, and there's Z associated to the edge, and defined by the condition for each polygon that the product is 1, and the action acts on X by whenever you have a vertex and it is incidence and there is sitting GV, and you have this ZV, then GV acts on ZV. This is a part of the structure that I started with. Okay. Yeah. So right, and this is so this is kind of general thing, and now we make it a little bit more explicit and more special. So our markings always, as I said, GV is B, and what is ZV? Well, we have to choose. We choose a permutation ZE. Z is for edges. Choose this permutation WE inside W, the while loop, and this ZE will be simply the corresponding cell in the as a subset of G. So So recall that we have a stratification. G is disjoint union of these cells. When W is this matrix, then this is a subset of matrices G inside G, such that GW has LU decomposition. So this is well known in linear algebra that, roughly speaking, every matrix has a decomposition into lower triangle and upper triangle, but their more special matrices don't. And then you have instead this stratification in general, right? And this ZE is so right. So you see that as a result, we have a recipe that to every polygonal surface plus map from edges to W, we associate with kind of global quotient stack. Okay, so let's even restrict further this example. This is already interesting when you have just a single polygon. And it's not just a cycle, it's a polygon. And we have some sequence of permutations. And then what this means that you have this subset of the W1, WK. So what is a subset? If G1 is here, G2 is here, GK is here, such G's such that G1, G2 product is 1. And B to the K acts as follows. When you have so B1 BK acts on G1 GK, where you you multiply G1 on the right by B2 inverse and on the left by B1, and similarly you multiply G2 on the left by B2 and on the right by B3. And this doesn't change the product. It conjugates the product by B1, and if it was identity, it remains identity. So this is the main example, and if in principle we care only about this example in this talk, but I just want to stress that you can put this stuff on arbitrary surface and get more interesting. So any questions for this? This is a sort of very explicit conception. Yes. Okay, now where are we in the plan? So so there is this relationship to Khovanov-Rozansky homology of the closure of this of L, where beta corresponds to simply the product of the generators of the braid group. And at A equals I think to be correct, it will be infinity. So there is always in Khovanov-Rozansky there is A equals 0 is A equals 0, and the complementary one where the top degree in A. And this is it. So we have this space, and this is I will call it folklore. But I'm happy if somebody tells me good reference. So the relationship is that the compactly supported cohomology, so compact supported homology, which is equivariant with respect to the group, which was called gamma. Gamma, remember, is this B k times, and you apply it to this space X. Is this this Khovanov-Rozansky of L at A. Okay. So the sketch of proof. So here is some little insight. So there are two ways to compute cohomology.
Sorry, do you need the equivariance for cohomology here?
What?
Do you need to take equivariant cohomology?
Sorry, I put gamma here. I mean, C stands for compactly supported, and putting gamma here means equivalent.
Okay.
And so one is by exhausting X from an empty set to the whole of X. So by exhaustion. And another way is to compactify X and removes by compactifying. And this is the second case. So there is a way to compactify so we can compactify X by relaxing. So first, assume that the Wi are transpositions. Wi, these labels on the edges are transpositions. And we can relax the assumption that so instead of Z you're right, you take which was BWIB, you replace it with the closure, and then you get this kind of variety which is now compact. And then you can use some properties of weight, filtration to see that cohomology of our X is actually a complex, can be computed by a complex where elements in the complex are cohomologies of this this kind of compact spaces. And then you will see that sorted by modulus are exactly cohomologies of this compact ones.
Do you need to know that ZIs are like normal crossing divisors or something like the complement?
I just give a sketch. Sorted by modulus are cohomologies of this of the strata.
If this is folklore, you should write it down.
And probably you need to, yeah, I'm sorry, this is not complete. Maybe I will write it down at some point. Okay, so there is this relationship which you may say, okay, let's conjecture it for now, but that's our motivation, right? So we have this identification of the Khovanov-Rozansky homology with cohomology of some space. So first we can look, maybe there is some extra structures associated with space, and it give us some extra structures. So what extra structures do we have on X? Well, it turns out, so this is quite, I don't know, very well known to some people, but not so known to others. So there is a way to write, so this Schubert cell can be written a little bit finer as some kind of, so B is upper triangular matrices. You can always write them as some upper, U is 1, 1. So unipotent upper triangular matrices. Then you can put here T. T is the torus. Then you have this W, and then you have some kind of part of U. So it's UW, some explicitly given subgroup of U. And then there is a map. Is a map from BWB to T. Yes. And then, so now forgetting like sending this X becomes, for doing it for every edge, you get a map from X to T to the number of edges. Right. But so it's basically this space associated to a polygon which is empty inside, where you put T everywhere. But the action is a little bit twisted of T on so you have this T sitting here, and there are T here and T here. So this action is twisted by one of them. If you choose one of them to be just multiplication action, then another has to be multiplication with a twist by W. T is twisted by these WIs. It's clear from this description. TW, when you write it as TW or you write it as WT, you have to apply W and permute some entries of T. So now I will just tell you what you get is that so this results in the following. So we have X, we can send it to T to the number of edges, which is K. And then, so remember that b to the k acts on x by these changes of yeah, for every vertex. And then there is tk sitting inside bk, which also acts on x. And then you can ask, so there will be another tk, and this, so this, sorry, let's b tk is goes here, and this acts, and the action, so this tk acts on this tk, and so obtain the map of from x mod b to the k to tk mod tk. And if you figure out this, figure this quotient out, you will obtain the following: obtain map from here to C star to the C mod C star to the C, where this action is trivial. So it's, you should think about it as a, you have this braid with C linked with C components. So you have circles, and there are C of them, and this thing here is local system on a circle, C star local system on a circle, which so it's C star modulo C star with a trivial action. So in this world of global quotient stacks, it means you have a map from space to the space and a map from a group to a group, which is commutative. So, okay. So you have this. And there is some little correction. So first, so they call this abelianization map. So the image of this abelianization map is not the whole torus. It is because whenever you multiply some matrices, determinant, if the product of is one, the determinant must product of determinants must be one. And this is a subtorus, which I denote by so it's contained. It is contained in the collection of T1, Tc, such that the product of Ti is 1, and this is T1. I denote this. No wait, T2. And another thing is, of course, you can think that if you conjugate every matrix by a scalar matrix, nothing changes. So this results in that not whole torus acts on X non-trivially. So in fact, diagonal C star in this system C acts trivially on X, and so T1, which is the quotient acts. Okay, so what does it give us on the cohomology? Does this give on cohomology? What kind of extra structures of X? So here I want to look at some simplified picture where we have some action of, so we have, let's say we have a space X and C star acts on X. And I want to replace, so let's, for simplicity, forget about this distinction about compact supported cohomology and normal, usual cohomology. For smooth spaces, they are dual to each other. There is no really much to lose. So just for simplicity, let's look at cohomology. So we have, let's say we have a space and C star acts on X. What can we do? We can do two things. The first thing we can do is we can consider the action map. This gives us a pullback on the cohomology. Sorry, not K, HI X to HI of X tensor with, sorry, HI of X tensor times C star. And then I want to use QNet decomposition and get the component to project to HI minus 1 of X tensor H1 of C star. Okay. And then contract contracted with the generator of H1 of C star. So yeah, generator of H lower one, let's say that we use the pairing to pair H1 cohomology with homology, and so we obtain a map to HI minus 1 of X. Right. So we obtained that homology of the group of C star induces a map, a degree minus 1 map on the cohomology of X. Then there's another way, another thing you can do. So equivariant cohomology. So HI of X, C star equivariant cohomology. Because sort of the quotient of X mod C star has some tautological line bundle. And this line bundle has a Chern class. So this has an action, as a degree 2 endomorphism. Multiplication by some first Chern class of some line bundle. Just so, or in other words, equivariant cohomology of a point. Okay, so there's these two things, and they should be related by the causal duality relates this and this. All right. I don't know if I made some mistake, but you see, so whenever you have a space with an action, you have choice. Either you take equivariant cohomology, which will have action of degree 2 generators, or you have usual cohomology, which will have action of degree minus 1. Now we have another situation. Now we have, suppose we have a map X and a map from X to the torus. Then, so you can again do two things. One thing is you can simply pull back the h1 of C star to h1 of x. So it gives some, I don't know, eta in h1 of x. And multiplication by eta is degree 1 map from from the cohomology of x to itself. This is sort of straightforward. But then there is another way, another thing you can do. But this is a little bit tricky to define in general. But suppose x is so nicely somehow smooth over C star. So I'm not saying what this means, but I want that cohomology of x gives us cohomology of fibers of x form a local system. So suppose, so this means that, well, I can say push forward or something, but so x t, where t runs to cohomology of xt, where t is on C star. So suppose is a local system. Is a local system. So that you know that so the cohomology of x doesn't have any jumps. Then you can smoothly move this point t. So then moving t around 0. So this is my C star. We have that there is obtained endomorphism of xt of degree 0 now. Because it's simply monogamy, it preserves every homology separately. Okay. And okay, so our homology is now not cohomology of the whole space X. It's only cohomology of the fiber. And so again, we have two pictures, and this is there is a big question. I don't know. This is worked out that there is causal duality connecting this one and two. In this simple case, I mean, in general, more generally, in this simple case, when this local system is simply is really a local system, then there is some way to relate the cohomology of the fiber to the cohomology of the total space, and that way will involve computing some kind of causal complex associated to this endomorphisms of the fiber, and that's why. So anyway, so this seems to be this sort of causal duality, maybe more general, maybe not. These are all these extra structures that I'm trying to list, and this is really some kind of symplectic duality. I don't know, in some situations, sometimes, imagine you have a symplectic form on X, so that X to C star is a moment map for C star acting on X. So now we want to have both a map to C star and an action of C star. And then omega should be a part of SL2 action on the cohomology. So SL2 first, SL2 action permuting maybe let's say this case A and this case B, permuting A and B. And that's the expectation, so to say.
How do you have a moment map to the group?
What? Sorry?
I mean, the moment map should go to Lie algebra. It shouldn't go to the group.
Yes, but if you remember the definition of the moment map, you only need its derivative. Right? And its derivative is in the Lie algebra. So you can say that this is a map to I know. So if you have this, so here is a definition of a moment map. You have X and you have C star times X to X. And this is action map. And you want that the pullback of this omega equals omega from X plus form where eta is on coordinate on C star Z X, and psi is coordinate C star on space on C. So which the other C star, the one where you have a map. That's correct. Equivalent to be one. So yeah. So here is this picture, right? We want to. The question is, maybe we cannot work this all out as it is stated, but maybe we can find all these features in the Khovanov-Rozansky homology. To find all these features in Khovanov-Rozansky homology of L. And this is what we will do. Now, maybe I will pause for some questions, and I have to put myself back in order.
Thank you.
May I ask a question?
Mm-hmm.
Maybe it relates to what you will tell us later. Can you explain how two C star actions work for a single unknot?
That.
So what is your variety to begin with? Is it just C?
The variety will be a point for the unknot. You want the product to be identity, so it's just point identity.
And it fibers. Now you say it fibers over C, and there is it fibers over C star, and there is a C star action.
Yes, but they're both trivial. So this is the case when C equals 1. because you start with the unknown.
How do you fiber a point over C star?
Or wait. Point is just mapped to the identity of C star. Yeah.
But this is not smooth in the sense you just described.
Yeah, you don't expect to get anything interesting.
Sorry, you don't expect to get anything from a knot?
Yeah, from so knots will not give you any extra structures, not much at least. You will see that there will be something, but symplectic form will be there, for instance. But from the point of view of these extra structures, it's not much.
Maybe it's not interesting, but I'm sorry. And how do you get the powers of x? So usually for unknot, you have powers of x. So if the variety is a point, I'm asking very simple question. I guess I missed it in your explanation.
If you have a variety which is
because it's point modulo C star.
It's a covariant homology of a point.
With
yeah,
respect
it's
to
a
C star.
polynomial.
No.
So it's a polynomial ring. This
With respect to C, I guess.
yeah, maybe okay. So unlink gives you on strength. You want unlink, you don't want unknown. But then so produces that x is a point. The action is trivial. So you obtain that the cohomology of x and the equivalent cohomology of x, which is this T1, is simply polynomials. And here you have a choice. You can, of course, add one more variable, or you can so C minus 1 or C, which connects to reduced, or no, depending on which. Okay. Now, the cohomology of x is just k. And so these odd variables act trivially. And this is sort of Cauchy duality. Now you can take this sort of cohomology of the fiber, which is not really well defined thing, right? Because there's no fiber in general points, because it's just a point. So it is a fibration consisting of points in equal point. But formally speaking, the equivalent cohomology of the fiber should be this polynomial ring in two sets of variables. And a non-equivalent cohomology of the fiber should be polynomials in only these variables. So this does make sense, because also you can think that monodromy is something when we pull back to the universal cover and take cohomology there. And if you think about pulling back a point over a circle to a point to the real line, you get the z points, z worth of points, and they all produce you elements in the same cohomological degree in H0, and that sort of matches this picture. Right.
How do you pull the back to universal cover? Like you have a map from a point to a point in a circle.
Point goes to S1, and then there is this universal cover R, and take fiber product, you get Z.
Okay.
You go to R. And if you consider the cohomology as a discrete set, it is.
Yeah, I guess you can do it in general then.
I'm not expert in this sort of abstract stuff, so maybe okay. So maybe it's worth to look at some example. Still in the remaining time, so you can choose some n equal 2, and then your braid is just t1 to some number of times. And then there is explicit way to write down this variety as you simply take products of matrices. And then you insert.
Not there. No, Z is not there.
Okay, or another way. Yeah, sorry, I'm tired. So do this. And this should be upper triangular. So this is subvariety, explicit subvariety of C to the K. And if so, if you start doing this, you get first something trivial. For instance, K equals 2. Z2, Z1, 1 plus Z1, Z2. So the condition says that Z1 must be 0, and therefore, so the map to C star is given by these entries, by reading of these entries. And it says again, you get the point. This corresponds to the Khovanov-Rozansky homology of Hopfling in A equals infinity is just one-dimensional. And so to get something more interesting, you should consider next case, K equals 4. You will have some kind of, all right. And also you notice that Z2 is somehow, you can gauge it out also. So Z1 forces it to be 0, and Z2 is sort of gauges trivial. It's not, just becomes direct product. Z2 is not interesting. Yeah. So in K equals 4, you will have subset of C4, which is something three-dimensional. Now, when you take quotient by, but because one variable you will see is not interesting, is obtain something two-dimensional. And this will be, this has a symplectic form, holomorphic symplectic form. And there is an action of C star. So, so sort of one of these two dimensions is acts. And also C star, there is a map to C star. So it looks like you have this C star, and there is sort of this our X. So it's X mod C star. Like this, but here in special point where it is 1 inside C star, there is a jump. And yeah, and I should have remembered which example this is. I think this is a complement of x is actually a complement of xy plus 1 equals 0 in C2. And C star acts by scaling xy to x lambda y lambda inverse, and a map to C star is given by this xy plus 1. And the form is given by dx raised to dy over xy plus 1. So if you want to play with this, then that's the simplest example. So but still you see that the you already have something smooth over C star, but it's still family of points. So not interesting again.
Why you have a family of points? Like you have all these fibers, like there will be family of hyperbolas.
Yeah, but right, it's a family of, but when you divide by C star, you get a family of points.
Anton, is this a good place to stop the lecture for today?
Yeah, that's right.
Great. So let's thank Anton. Now we can continue asking questions. I was going to ask what you meant earlier when you said that SL2 interchanged two things.
Yeah.
I know that part's all like vague stuff anyway, but I think it was earlier still, but maybe you have this.
So one thing will be something like you have equations, something like this. I, and there will be some kind of Lefschetz-like operator. F, so that F omega is omega and some H.
So omega is like the derivation, bracket with omega is like the derivation sum over I, xi ddyi.
Yes. Mm-hmm.
Great.
And then, so if it's, so if there is SL2 triple, then automatically you will have that F xi will be also yi. And in this sense, SL2 rotates them.
But even if you don't know SL2, like you're saying that all your conditions on the form just imply that the commutator of omega and yi is xi, basically. Like this equation, you don't need Lefschetz or anything.
Yeah, the other thing is yi ddxi, right?
Yeah, right. So the intuition behind this identity is that omega should be like some xi dyi, and this is our E. And F, well, it's up to some constants. You should exactly. And H should be something like xi dxi minus yi. Sorry for that. But if you have seen this, you will recognize. Yeah. Yeah, so I think I will. So I was planning to, next talk will be about Khovanov-Rozansky homology and details on the construction.
So is it? I mean, I as you maybe know, I love to think about SL2 actions just on the X part. You know, for instance, if you kill all the Y's and just look at the X's, then the sum of xi squared ddxi is a raising operator, and the sum of ddxi is a lowering operator. Do you have any intuition where those operators might come from? Or maybe they come from some specialization relating y and x or something?
So since we have, we have a name. Well, I think, I mean, I kind of, he helped us to a little bit identify this thing. There is an algebra, which n is algebra of polynomials on C2 is Poisson bracket. And it has obvious basis. X squared, y squared, y cubed. This algebra, turns out, appears a lot in algebraic geometry. At least its deformations are these W algebras that act on cohomologies of Hilbert schemes of surfaces, and so on. So it's not an entirely surprising algebra.
Where does the subscript n come from?
Oops. No, that is, I'm confusing two things. Thank you. Right, so you can sort of draw. Then you can see many SL2s. So one is, this is our SL2, and this is Ben's SL2. If you want, this whole thing is Virasoro. Half of Virasoro sitting inside, I think, contains this one too.
But this whole H2 should act?
Sorry?
This whole H2 should act?
Yeah, so conjecturally, H2 or some of its deformation. And of course, H2 is generated by this 1x xn and let's say y squared.
So what's the motivation for the appearance of this algebra?
Say again?
What's the motivation? I mean, conceptually, why should H2 appear? And so somehow it's a Poisson algebra?
Right. So this algebra acts on, the motivation is that H2 acts on things like Hilbert scheme.
Just on the space or on some related structure?
As a Lie algebra.
On cohomology.
No,
I mean, it also has X on the space. Yes.
X on C2 first, yes? So
Yeah.
as a space. By Hamiltonian, well, how do you say? Hamiltonian vector fields. So it's an infinitesimal action on the space. Infinitesimal. On C2, and therefore on Hilb and C2, and also it acts on some various natural bundles on Hilbert scheme. And since we know that Khovanov-Rozansky cohomology is related to Hilbert scheme, you can say this is one motivation. So by this, all these conjectures and work of different people. So, for instance, more precisely, cohomology of some power of a full twist is given by, so y-ified is given by global sections of a bundle on Hilbert scheme. Of some bundle, which I need to try to figure out properly. Something like P twisted by K. There are versions more general, but so H2 acts on this.
So if you take the algebra of Hamiltonian vector fields, so just very trivial question, what's the relation to polynomials and two variables? So you have vector fields in two variables, you kind of convert this to polynomials in two variables.
It's a little trick I was using. The point is that if it's if Lie algebra X on X, it also acts on X times X n times. So
no, I think the question is, if you have a function of x and y, how do you produce a Hamiltonian vector field with space?
Oh. So if you have a polynomial x to the I, y to the j, then you have to write f, then you write d over d, df over d y times d over dx, I think, minus df over dx, d over dy. So this is a differential operator. It acts on as a vector field on C2. But on for instance, on C k times, you would write sum of. So you just repeat it and k times. So for instance, this would be j x to the I, y to the j minus 1, d over dx. And you insert some index m everywhere, and you sum over m. Now, from 1 to k. So minus I, x m, I minus 1, y m j, d over d y m. And this is now on C 2k. Right? So you have these vector fields. Now you can explicitly write.
In particular, it acts on homology of unlink with this formula. So homology of unlink is just polynomials in x's and y's, and this is the formula how they act.
So can I just, like, going back up to this previous example of where the y's first appeared, they sort of really showed up when you had this this case where the image of x under the map to the torus was just a point, or in other words, where the C star action was where the map to C star was trivial. And so like this extra y variable is showing up because of the triviality of that in some sense. Like if it actually was smooth, you wouldn't have these extra y's.
you will have
Not be
some,
the y's because there's some traveling to the universal.
you get some usually unipotent action of the y's.
I see. I see. Okay. You still have them, but okay, got it. See, I was just trying to figure out why, and I'm like, this is sort of a convincing reason for why this algebra should act on Khovanov-Rozansky homology, but I still sort of want an explanation for why it should act on the Hecke category itself, or whatever the y-ification. Anyway, I'm going to stop the recording now. By the way, so, well, I'm going to thank Anton again.
Thank you.